Okay, welcome to a super important topic in mathematics. It's one of the most important topics you'll ever cover in advanced math. It's introduction into differential equations. So this isn't gonna have a ton of applications in this video, but once you get super good at differential equations, you're gonna be able to do lots of super cool stuff. So let's just get right into it here. So hopefully by now you know what a derivative is, right? So if we have a graph, right? Let's say looks like this, kind of a parabola looking thing. If our graph is f of x, right, we know that f prime of x is going to give us our slope at any point. So if say like this is 2 right here, f prime of 2 is going to be the tangent to the graph at the point x equals 2. F prime of 5, let's say that would be over here, right? It's just going to barely kiss the graph at this point. That's what that tangent is. So that's what a derivative actually is, and you can go over the definition of a derivative and using limits to find what the derivative is, but that's kind of the basic idea. Now that we know that, we can kind of dive into something deeper with more significant implications called differential equations. So a notation like I just wrote f prime of x, right? F prime of x, that's kind of the easiest way to write it, but I actually like to write it this way even more. I like to write it dy, right, by dx. And I like this because this dy is kind of referring to a nudge in the y direction, and this dx is referring to a nudge in the x direction. So remember when you first started to learn about functions and graphs, you did the slope was equal to the rise, right, over the run. And this is equal to the change in y over the change in x. And this is honestly the exact same thing. The only difference is this only works with straight lines, so it doesn't matter how big the nudge is. This dy by dx is saying the nudge is infinitely small. It's an infinitesimally small nudge, right? Like you can't even tell that the nudge is there. It's so small, but this is how the function is changing at that exact point in regards to the nudge in y and the nudge in x. So that's kind of how I like to think about it. Okay, so um, we can actually do some pretty cool stuff if we know uh, what dy by dx is. So let's say dy by dx is equal to x for some function, right? This isn't f of x. This is dy by dx. This is what the slope of the function is at some x value. It's equal to x. Okay, so how can we figure out what f of x is if we know dy by dx? So we have to use kind of our knowledge of integrals, right? Because the inverse operation of differentiation is integration. So if we integrate both sides, right, we take the indefinite integral, right, and we have to multiply both sides by dx. So even before we integrate it, I'll give myself more room here. Equals x. So if you multiply both sides by dx, right, then this dx goes away. So we have dy equals x dx. And now we can integrate both sides, right? Take the indefinite integral, and the integral of dy is just y, right? And the integral of x, right, we just use the power rule. That's going to be 1/2 x squared plus some constant. This constant is here because we always have to add it after we take the indefinite integral of some expression, because if we differentiated this, like even if this constant was, let's say it was 5, if we differentiated this, we would get x. We would get y, or we'd get dy by dx equals x no matter what the constant is. So we just have to add this plus c, we can only figure out what C is if we're given some initial condition. If we know what a point on the graph is, so we can plug in our y, we can plug in our x, and solve for C. So in this question below, I'll give you the initial condition, and we'll be able to solve for what C actually is. Okay, so the question is, solve dy by dx equals sine x subject to the initial condition f of 0 equals 3, or f naught equals 3. So whenever it says solve the differential equation or solve dy by dx, that's saying, okay, here's what dy by dx is. Figure out what the actual function is. What is it referring to? So we're going to set it up the same, right? Dy by dx equals sine x. Okay, we multiply both sides by dx. This cancels here. So dy equals sine x dx. And right, we integrate both sides to get rid of that dy and make it just y. So we have y equals, that's always what we want. We want y equals. What's the integral of sine? Well, it's going to be negative cosine x. And we don't end here, right? We've got to add that plus c. Because if we went in the opposite direction and we differentiated this, right, we would get positive sine x, and the c would disappear no matter what it is. So we're not quite done because they told us that the initial condition f of 0 was equal to 3. So that means that the function was equal to 3 when the x value was 0 plus c, right? So what's cosine of 0? Well, that's going to be 1. So negative cosine 0 is negative 1, right, plus c. And now from here we just add 1. So 4 equals c. Now instead of negative cosine x plus c, we can just write negative cosine x plus 4. So this function right here, it meets all the requirements. If we differentiated it, we went backwards, we would find that dy by dx was in fact sine x, right? Because the derivative of negative cosine x is sine x. And we would also find that if we graph the function itself, f of 0 would be equal to 3, and that meets the subject that's subject to the initial condition, right? That requirement there. So that's just an example. That's kind of an introduction into what differential equations are. In my next video, I'm going to talk about slope fields and why they're useful, because you're not always going to be able to algebraically solve for the function. You can get pretty crazy. This is kind of a basic example, but this is just kind of some intuition, some insight into what differential equations are, right? We're given dy by dx, we multiply by dx on both sides, we integrate it, and we get our function back. Okay, so like I said, it's not always going to stay this simple, but this is kind of an introduction. I'll see you in my next video.